Thank you for giving me the opportunity to present this talk. I'm sorry about the about not being in Bordeaux and about the technical issues. But today I will present you our results on the carbon chain molecules towards massive clumps. And first, I would like to explain you the molecular complexity and how we came to this project. So the molecular complexity at first was used for the complex organic molecules, which are molecules with 6 or more atoms. And it was first observed towards dense and hot medium, that we call the hot cores. But after that, it has been observed towards hot corinos, prestellar objects, or diffuse clouds, which are objects with a lower density or also a lower temperature. However, recently, the study of the unsaturated complex molecules at low frequency using the GBT and YEBES opened a new cold chemistry and cold complexity. And so these studies targeted the TMC1 dark cloud, and they observed some extremely rich chemistry towards carbon chain molecules, but also ions and cyclic molecules. And however, this carbon chain chemistry was also studied towards low mass objects, and where they found a dichotomy and between the hot corino chemistry and the warm carbon chain molecules chemistry. And in some objects, the hot corino chemistry and the clumps were observed, while in other objects only the carbon chains were observed. And during several years, it was considered, these two chemistries were considered to be exclusive. However, recently, several objects have been observed where the two chemistries are observed. Also, some objects with none of the two chemistries were observed, so it's questioned the chemical pathways that we might have in the star-forming regions. And in this big picture, we wondered how it's going into in the high mass star-forming regions where clumps were observed and are observed for many years. So the first observations were done a couple of years ago with ALMA, and it revealed that the cyanopollines, and in particular HC3N and HC5N, were observed close to the protostars and in a really hot region around the protostar. And it led the team of Taniguchi to draw a sketch of the possible scenarios for high mass young stellar objects where you have either hot core chemistry with many clumps, or a hot carbon chain chemistry, where you have these carbon chains, but observed in a hot medium and above 100 Kelvin. So in this big picture, we decided to do spectral surveys at low frequencies. And for this, we used the YEBES and Effelsberg telescopes in the Q band and the IRAM 30-meter telescope in the 3-millimeter band. So the targeted sources were at first 3 clumps, tracing various evolutionary stages from the infrared quiet regions to the H2 regions. We selected these sources using the Atlas-Gal survey, and we wanted to trace different conditions during the high mass star formation to be able to understand how we form these molecules. So you can see here, I don't know if you can see my mouse, but you can see it here on this slide, the detection of some cyanopollines that we detected using YEBES and the 30-meter. You can see that they are well detected. And our multi-wavelength study gave us the opportunity to really make a full analysis of the physical parameters of these lines, and to have robust estimates of the parameters thanks to the multiple lines that we had. So we had clear detection of HC3N, HC5N, and HC7N, and I will now focus on this. We had several lines, and we were able to perform non-LTE modeling of these molecules using the CASIS software developed in Toulouse. And thanks to this modeling and to the detection of the lines that we had, we could estimate the temperature and determine the line width also of this emission. And the temperature that we obtained revealed temperatures between 20 and 30 Kelvin, which is much lower than what has been observed towards other high mass star forming regions. And where they observed temperatures of 100 Kelvin, which suggest potentially different chemistries. However, this temperature is also extremely different to what has been observed towards the low mass star forming regions, where the carbon chains are usually detected around 10 Kelvin. So we need to keep this in mind. The low line widths that we also observed for these molecules suggests that we are also in the quiescent gas in these regions. And now, if we compare the column density ratios that we obtained for these molecules to what has been observed and what is available in the literature, we can see here the comparison. So you have the HC5N over HC7N column density ratio for all these sources. And here you have the last three sources are the sources that we targeted. And you can see that this ratio is almost constant and within the error bars of our measures. And when we compare to what is available in the literature, we have something which is constant. And we highlighted here TMC1 and L1527. So L1527 is a typical warm carbon chain object. And so we can see with this that the chemistry that we have for HC5N and HC7N in our objects is not that different from what is observed towards these two objects. And one other thing that we can see here is that we have different luminosities between the low mass objects and the high mass objects. And we have at least an order of magnitude of 2 to 3. And we see that the luminosity does not have an impact on this ratio. And if we look at the models, so here are some models done for TMC1. And you can see that the heavier the molecule gets, the lower the abundance of the molecule is. And so this is what we observe. This is their results are consistent with what we observed towards our high mass star forming regions. And their interpretation of their model is that to have a gas the carbon chains can form through gas phase reactions, and to be able to see them in the interstellar medium, the object have to be either very young, and the atomic C is still being able to form, is not yet completely under CO, or either the carbon was already released from CO. In our cases, because we trace so many different parameters, we are not able to differentiate between these two conditions. So because we had several models available for a more in-depth study, what we did is that we observed, we did more observations, and we took archival data towards 40 sources. We have adopted the same idea, is that we wanted to trace different physical conditions. So we used these 40 sources are distributed over the same types of region and are also selected from the Atlas Gal survey. However, for these measurements, we have only IRAM 30-meter data. But what we can already detect is and see is that we have many types of carbon chains. So far, I studied, we focused only on the cyanopolynes, but here we can see that we have the other types, the linear and cyclic molecules, and also the carbon chains with sulfur atom, which are a bit different. We do not have heavier molecules, but this is also due to the upper level energies that we are covering. So we were not surprised by the fact that we do not have over molecules. And what we saw when we measured the abundances of all these molecules in all the objects, and we compared them to low mass objects, is that we have similarities. So here what we can see is the ratio between the abundances, the average abundances of all the objects and the high mass star-forming regions over the abundances that we observed towards TMC1, L1527, L483, and IRAS 16293. So the first two, I already mentioned them, but L483, it's an object in between where we observed hot Corino chemistry, but also this warm carbon chain chemistry. And IRAS 16293 is the typical hot Corino. So we wanted to see what we have, knowing that we have a large emission of clumps already in these objects. And what we can see is that for some molecules, obviously, we have resemblances between between our objects and TMC1, but also between our objects and L483. However, for all the molecules within a factor of 5, we resemble L1527. So for these molecules, our results show that we have similarities between high mass star-forming regions and the WCC objects. And this leads me to my conclusion about for the cyanopolynes that we studied in detail, and we could see that they are well detected for the simplest one, for HC5N and HC7N. However, we have a temperature of 20 to 30 Kelvin, which is not similar to what has been detected before. And we see similarities between the carbon chain-rich sources and what we observed in high mass star-forming regions. However, more modeling is needed. And when we go to a broader picture, the first results of our studies shows that we have many carbon chain molecules detected in the cold envelope, and that we have similarities with the WCC chemistry. Thank you for your attention.